Hello everyone, I want to continue chapter 23 today. Okay, we talk about the plane mirror, spherical mirror. In our last lectures, we talk about the convex mirror, we talk about the concave mirror, and we also write down the equations 1 over f. F is the focal length. This is equal to 1 over this of 0, this is object distance, plus 1 over this of I. Okay, so this is the mirror formula. This is the mirror formula. Okay, and here f, this is focal length, this of O, this is object distance, and this of I, this is image distance. Okay, and we also have to use the sign convention. When you choose the positive sign and when you choose the negative sign. For example, you have to measure the focal length, you have to measure the radius of curvature, you have to measure the object distance, you have to measure the image distance, like this. Okay, so the focal length and radius of curvature of concave mirror is positive. The focal length and radius of curvature of concave mirror is positive and convex mirror is negative. Or simply you can say that, like, this is your concave mirror, and if you draw the, let's say this is the focal point, here you have a center of curvature. Now look, this is the focal length, little f, and this is your radius of curvature r. The focal length and the radius of curvature in case of concave mirror is in front of the reflecting surface, or simply you can say that in front of the mirror. So if the focal length and the radius of curvature is in front of the mirror, that is positive, and the focal length and the radius of curvature of concave mirror is in front of the mirror. That is why I said here the focal length and the radius of curvature of concave mirror is positive. And convex mirror, look at this, this is convex mirror, and this is your principal axis. Right here you have a focal point and here you have a center of curvature. So this is your focal length, little f, and this is your radius of curvature r. Now you can see that in case of convex mirror, the focal length and the radius of curvature of the convex mirror is behind the mirror. That is why the focal length and the radius of the convex mirror is negative. So if you need to solve the problem, always keep in mind the focal length and the radius of curvature of the concave mirror is positive, and the focal length and the radius of curvature of the convex mirror is negative. So this is number 1. And number 2, if the object distance and image distance is in front of the reflecting surface or in front of the mirror, that is positive. The object distance and image distance, they are positive if they are in front of the mirror and negative if they are behind the mirror. Okay, so if the object is in front of the mirror, of course object distance is positive. If the image is also in front of the mirror, then of course image distance is also positive. But if the object is behind the mirror, I don't think that will be the case. But if the object is behind the mirror and if the image is behind the mirror, then in that case the image distance is negative, object distance is negative. Okay, so please keep this in mind. The sign convention is also important to solve the numerical problem. And the important equation here is the mirror formula, 1 over f equal to 1 over object distance plus 1 over image distance, and the another formula is the radius of curvature r is 2 times the focal length. Okay, so this is also the formula. Okay, in my last lecture I gave you the homework assignment, like to draw the ray diagram. Look at this. Let us suppose this is your concave mirror. This is the concave mirror, and this is the principal axis. This is the pole of the mirror. You can call O. Right here you have a focal point, and right there you have a center of curvature C. And you know that the focal length OF is the focal length and OC is the radius of curvature, and you know that OC is 2 times the OF. And my question was, if you keep the object here, let me call this is O prime object, or you can use, since you have an O here, you can use different name, that is not a big deal. So let me use A and B. So AB is the object. So did you draw the ray diagram? What happened in this case then? Where is the image? Okay, one ray you can take from here, and it is parallel to the principal axis. After reflection, this ray, it passes through the focal point like this, focal point. And how do you draw the second ray then? I told you that to form the image you need at least 2 rays. So what do you think? How do you draw the another ray? You can take like this. Right there. This is incident ray, and the reflected ray goes like this. You can use the ruler and protractor, okay? So look at this. These 2 reflected rays, they are parallel. These 2 reflected rays, they are parallel. So where is the image then? Where do they meet? The reflected rays, these 2 reflected rays, where do they meet? So if they are parallel, we consider they meet at infinity, somewhere here. Somewhere there at infinity. So here the image distance is infinity. This of I, this is equal to infinity. This is equal to infinity. If you keep the object, I think you can try from here. So 1 over f, this is equal to 1 over d of O plus 1 over d of I. Look at this. So 1 over f, this is the focal length of the mirror. What is object distance here? Because object keep at focal point. So object distance is focal length. So it is 1 over f. Object distance here, d of O in this case is equal to focal length. So 1 over f plus 1 over d of I. Okay. So 1 over f minus 1 over f, this is equal to 1 over d of I. Okay. So this is 0 equal to 1 over d of I. So what is d of I then? What is d of I? So from here you can get d of I, this is equal to infinity. Okay. So if you keep the object at the focal point, your image is at infinity. And the image here, image is image formed at infinity d of I equal to infinity, image is inverted, real and magnified. Okay, so this is the case if you keep the object at the focal point. And the another homework I gave you was this. Again, let us draw the concave mirror. This is the concave mirror, and here is the principal axis. Okay, here is the focal point F, here is the center of curvature, and you keep the object right here inside the focal point. Let me call AB. AB is the object. Okay, one ray you can take like this, parallel to the principal axis, and after reflection it goes like this. This is the reflected rays. Another ray you can take this way, and the reflection takes place like this. Now look at this. This reflected rays and this reflected ray, two reflected rays, this and that, they diverge. Look here, they diverge. They never meet on this side. If they are parallel, they can meet somewhere at infinity, but they diverge, so they never meet. So in this case, you have to extend this line like this, and extend this line also, dash line. Now these two rays, they meet here then. So this is your image A prime, B prime. So in this case, image formed behind the mirror. Here in this case, image formed behind the mirror. Okay. Image is upright. Image is upright. Virtual image and magnified. Okay, so this is the case I asked you in my last lecture. Okay, so this is all about the concave mirror and convex mirror. Please recall your last lecture also. Next topic, we are still in chapter 23. Next topic is refraction of light. Refraction of light. Before defining the refraction of light, I want to define index of refraction first. Index of refraction, this is simply represented by n, and the index of refraction n, it is really simple. Index of refraction is the ratio speed of light in a vacuum. We simply represent it by little c, speed of light in a vacuum, divided by speed of light in a medium, little v. Speed of light in a vacuum c. Light has a speed at, in a vacuum, that is c. It is 2.99 times 10 to the power 8 meter per second, or roughly you can use the speed of light is 3 times 10 to the power 8 meter per second. This is the speed of light in a vacuum, or in the vacuum or in the air also. In vacuum or in air also we use the same number. In the air we also use the same speed of light, but in the medium the speed of light is different. in the medium, like the speed of light in water, the speed of light in a glass, they are different. Okay, so the ratio speed of light in a vacuum C and speed of light in a medium like a water, glass, or whatever medium you have. So this ratio N, this is equal to C divided by V. This ratio is called as the C over V, which is represented by N. This is called as the index of refraction, or people they also call a refractive index. Refractive index. Refractive index. And different material, they have a different refractive index. For example, there is different types of glass. Okay, the glass has roughly 1.5. The index of refraction of glass is, I think it is 1.5. You don't have to memorize, it is given. Like ethyl alcohol, like if you calculate the refractive index of ethyl alcohol is 1.36. Glass, there are different types of glass. Different types of glass, they have a different. So simply, one type of glass, I don't remember. Glass, simply I can write down 1.5. It has no unit. It is the ratio of the same quantity, ratio of the speed. Speed of light in the vacuum, speed of light in the medium. So no unit, ratio, dimensionless quantity. So glass is 1.5, ethyl alcohol is 1.36. I think water, refractive index of water is, I think it is 1.33. You don't have to memorize this. Okay? Normally it is given, or you can calculate using the speed or using some other formula also. So this is what we call the index of refraction or refractive index. Now let us define what is refraction of light. Let us suppose you have a transparent medium. This is water. Water is a transparent. Water is the transparent medium. You know, we have a different type of object, like one is transparent object, other one is opaque object, or other one is semi-transparent, or you can also call translucent object. Okay, so we have three types of object: transparent, opaque, semi-transparent. Transparent object, light can pass through the transparent object. This glass you see, this is transparent, the glass here, light can pass through it, then I can see you. This is transparent. Or glass, normally the glass, they are transparent. Water is also transparent. Some kind of plastic also, they are also transparent. If you see, like this is a plastic, if you see the other side, yeah, this is a transparent. Okay, but opaque object, light cannot pass through it, like this. This is opaque. If I look at this, no, I cannot see you. This is opaque. Light cannot pass through this object. This is an opaque object. Wood, opaque object. Sand, opaque object. Many paper also, they are opaque object. Light cannot pass through the opaque object. And there are semi-transparent. Light can pass partially only. Like some kind of glass, I don't remember, some kind of glass that you can see only partially. That is semi-transparent, or you can call translucent. Or I think if you the wax paper, or if you keep the paper like a printed paper in the kerosene, you know the kerosene, then look at that, then the light they can pass partially. I don't have a kerosene here, so I cannot do that, but the kerosene that is like a petroleum goods. So if you put the printed paper inside the kerosene, that is a liquid, and take the paper out, then if you see, you can see partially. That is your semi-transparent object. Anyway, if the object is semi-transparent, light can pass through the semi-transparent object partially only. So here I have a water, and this is air. Here you have a air. Let me call medium 1. medium 1, and this is water, medium 2. Let us suppose the index of refraction of medium 1 is n1, index of refraction of medium 1 is n1, and index of refraction of medium 2 is n2. Now what happened is, let us consider the light is coming from here, from the source. Light strikes here. This is the incident ray. IO is the incident ray. And you can draw the normal right here. This is the normal, you can call N, O, N prime. This is the normal. So at point O, look, here water, different media. If there is no water, you know that light propagates in a straight line like this. Light goes in a straight line like this if there is no water. If there is no water, light propagates in a straight line, because light always propagates in a straight line, I told you. Okay, but there is a water, different media. So what happens is light bent here like this, like this. OR is the refracted ray. So what happens? Light bent here. Light bent here. So this bending of light as it travels from one medium to another medium, that is called as the refraction of light. So if you want to write down, you can write down like this. The bending of light, the bending of light as it passes from one medium to another medium. Is called refraction of light. Refraction of light. So simply the bending of light when it travels from one medium to another medium, that is called as the refraction of light. Okay, so here IO incident ray, IO incident ray, and OR is refracted ray. IO, this is incident ray. OR, this is refracted ray. Okay, NON prime, it is the normal. NON prime, this is normal at point of incidence. Normal at point of incidence. NON prime, normal at point of incidence. Okay, and this angle I can call theta 1, and this angle right here, this angle here, I can call here, this angle is theta 2. You can call theta I and theta R also, it's up to you. This is theta 2, this is theta 1. So theta 1, look here, theta 1, this is angle ION prime. ION prime. That means angle made by the incident ray with the normal. This is called as angle of incidence. Okay, and theta 2, this is angle NOR. NOR. This is called as angle of refraction. Okay, and what is N1? N1 and N2. N1, you can write down, N1 is the index of refraction of medium 1. In this case, the medium 1 is here. Okay, in medium 1 is here. And N2, this is index of refraction of medium 2. So you need to define all parameters. What is theta 1, what is theta 2, what is n1, what is n2, what is incident ray, what is refracted ray, like that. Okay, then we can define the laws of refraction. Okay, so I have to erase this. So let me state the laws of refraction. Laws of refraction. Okay, the very first one, the first law of refraction, we also call it as Snell's law. Snell's law. It is very simple. The first law is, it is experimentally established n1 sine theta 1 equal to n2 sine theta 2. This is the Snell's law. You have to draw this diagram. n1 sine theta 1 is equal to n2 sine theta 2. This is the first law of refraction of light. We also call this Snell's law. First one. The second one is similar to the law of reflection. So IO incident ray, OR refracted ray, and normal NON prime, all they lie on the same plane. Okay, so the second law is the incident ray that is IO, the refracted ray OR, and the normal at point of incidence, which is NON prime. The incident ray IO, the refracted ray OR, and the normal NON prime lie on the same plane. You can call this is the second law. Okay, and there is one more, but before writing the third one, I want to erase this. I want to draw a new diagram. Look at this. The third one is, let us suppose this is water, and here this is air and this is water. Air is, we say, optically thin medium. The density of the air as compared to the water is smaller. Okay, here this medium we call optically thin medium. Air is optically thin medium, or you can call also rarer medium. The density is less. Air optically thin medium, or you can call rarer medium, and water, this is optically thick medium, or you can call denser medium. The density is high, denser medium. As compared to the air, the density of water is more than density of air. So let us suppose light is traveling from air, optically thin medium, to the optically thick medium. What happens in this case is the light bends toward the normal. Look, it goes this way. The light bends toward the normal. If the ray of light is traveling from optically thin medium to optically thick medium, it bends toward the normal. Okay, so let me write down that. I can write down right here, number 3. If the ray of light is traveling from optically thin medium to optically thick medium, it bends towards the normal. But what happened? Now forget about this part, forget about this I, O, this is R. Right here, if you consider, this is water, what you have air here then, right? So water is optically thick, air is optically thin. What happened right here then? This point, right here, you draw another normal here. What happened in this case? Look, if you consider OR incident ray, this ray, OR is the incident ray, if you consider only this portion, forget about this part. If you consider only this part, OR incident ray, and this is air, optically thin medium, water, optically thin medium. So if the light is traveling from optically thick medium to the optically thin medium, in that case, the ray move away from the normal like this, bend away. Here, optically thin to optically thick, the refracted ray come closer to the normal. But if the light is traveling from optically thick medium, that is water, to optically thin medium, that is air in this case, the refracted ray move away, it goes that way. Look, it move away from the normal. Okay. So if the ray of light is traveling from optically thin medium to optically thick medium, it bends towards the normal. But if the ray of light is traveling from optically thick medium to optically thin medium, it bends away from the normal. Okay, so these are the laws of reflection. First law, you can call it Snell's law also, n1 sin theta 1 equal to n2 sin theta 2. The second law, the incident ray, the refracted ray, and the normal, they lie on the same plane. And the third law, if the ray is traveling from thin medium to thick medium, it bends toward the normal. And if the ray travels from thick medium to thin medium, it bends away from the normal. So these are the laws of refraction. Okay. Now look at this. Where do you see the refraction of light? Let us suppose this is a pond. Okay, and here you have water. Let us consider the fish is right here. This is considered the fish. Okay, this is fish. Fish is right there. And you are standing somewhere here. This is somewhere here. You have your eye somewhere there. So what happens is, if the ray is coming from here, like this way, what happened right here then? Light is traveling from thick medium to thin medium, so it bends away from the normal, so it goes like this. And another ray, if you draw like perpendicularly, like another ray, if the ray goes perpendicularly, it never deviates, it goes in a straight line. So where do you see the fish then? Look, right here the light is bending here. So the real position of fish is there. But look, let me call this is O, whatever you call, object O, you can call A or whatever, B, whatever you call. Now if you extend these rays, you see the fish right here. The real position is here, but due to this bending phenomenon, look, you see the object fish right here. The fish appear to be there. in real, the fish is here, but you see the fish right there. And if you try to catch here, of course you cannot catch that because the real fish is here. This is due to the refraction of light. Or if you want to observe this, take a stick and go to the light. If you take if you take a rod, let us suppose this is a rod, and go to the swimming pool and put this rod in the swimming pool about half, then you can see that the rod is straight. But if you put this rod in the water, you see that this rod is bending. That is also due to the refraction of light, because when the light travels from one medium to another medium, it bends, and this is a refraction of light. Why? Why we observe the refraction of light? Because in different medium, the light has a different speed. In the air or in the vacuum, it is 3 times 10 to the power 8 meters per second. But in different medium, water, glass, it has a different velocity. The velocity is changing. That is why the light bends when it travels from one medium to another medium. Like this is a glass slab. This is a glass slab. When the light travels from here to the other side, of course the light bends. This is a glass slab. Okay, transparent object. This is the lens. In this case also we can observe the refraction. Okay, so this is about the refraction of light, but I will talk a little bit more. So the third law of refraction, I told you that when the light travels from optically thick medium to optically thin medium, the ray of light bend away from the normal. So what happened? Look at this. Let us suppose this is water. This is water, optically thick medium. Optically thick medium. This is water. And this is air. And let me draw the normal first. This is a normal, N, O, N prime. And I take the ray, this is I1, incident ray. Light travels from water to air, optically thick medium to optically thin medium. What happened in this case? The light moved away from the normal like this. This is R1. OR1 is the refracted ray, not a reflected, refracted ray. Now if I take another ray like this, let me call this is I2. What happened? It goes this way then. This is R2. If you increase the angle of incidence, now let us take I3 like this. This is I3. Let us suppose the refracted ray is this. This is the refracted ray, this one everyone. This is R3. Now look at this. The R3 and normal. This angle here is, what is this? This is angle of refraction. Angle of refraction is 90 degrees. Look at the OR3. This is the refracted ray for I3O. Incident ray is I3O, refracted ray is OR3. And if you measure the angle of refraction here, it is 90 degrees. Angle of refraction, this is in the optically thin medium. Now if you measure this angle, corresponding angle of incidence in optically thick medium, if you measure this angle is called as the critical angle. And critical angle, this one, okay, this is angle of incidence, and this angle is called as the critical angle, and critical angle is simply represented by theta C. Theta C, okay. So let us define that critical angle, and it is simply theta C. So what is critical angle then? It is very simple. Critical angle is angle of incidence in optically thick medium. When the ray of light is traveling from optically thick medium to optically thin medium, light bends away from the normal. That is from laws of refraction. Okay. And if the angle of refraction in optically thin medium is 90 degree, if the angle of refraction in optically thin medium is 90 degree, the corresponding angle of incidence in optically thick medium is called critical angle theta c. If angle of refraction in optically thin medium is 90 degree, then the corresponding angle of incidence in optically thick medium is called as the critical angle. That means the ray must travel from thick medium to thin medium. And let us consider the optically thick medium angle of the index of refraction is N1. N1 is the index of refraction of optically thick medium, and N2 is the index of refraction of optically thin medium. And here angle of incidence is theta c, and here angle of refraction is 90 degree. Now if you apply the Snell's law, what is Snell's law is? Snell's law is N1 sine theta 1, this is equal to N2 sine theta 2. This is the Snell's law. Now here, okay, N1 is this water, N1 index of refraction of water in this case, sine theta 1. What is your theta 1? This angle is theta 1, but here I represented by theta c. So here theta 1 is theta c. Sine theta c, this is equal to N2. N2 in this particular case is air, and the index of refraction of air is simply we take 1, okay? We take 1. The index of refraction of water is roughly equal to 1. So N2 is 1 sine theta 2. What is theta 2? Theta 2 is this angle of refraction, which is 90 degree here. 1 times sine 90 degree, okay? N1 sine theta c, this is equal to 1 times, what is sine 90 degree? Use your calculator. Sine 90 degree is 1. So it is simply 1 times 1 then. So what is 1 times 1? Of course 1. So you can write down N1 sine theta c equal to 1. Sine theta c, this is 1 over N1. N1 is the index of refraction of optically thick medium, that is water in this case. So if you want to calculate the critical angle theta c is sine inverse 1 over N1. Okay, so this is the formula to calculate the critical angle. Theta c is equal to sine inverse 1 over refractive index. So N1, if it is water, plug the index of refraction of water here. If you want to calculate the critical angle for glass, you have to use the index of refraction of glass here. Okay, so this is the formula to calculate the critical angle. And if you know the critical angle, you can calculate the index of refraction also. If you know the index of refraction, you can calculate the critical angle, or if you know the critical angle, you can calculate the index of refraction. Okay. Now look at this. If angle of refraction here is 90 degree, the corresponding angle of incidence is called as the critical angle. But what happens if you take another incident ray from here like this? This is an incident ray, and let me call this is I4. What happens then in this case? If your angle of incidence in optically thick medium is greater than critical angle, what happens in that case? Think about it. If your angle of incidence in optically thick medium is greater than critical angle, In that case, simply the ray of light gets back to the same medium like this. Goes from water and it gets back to the water. It is not a refraction. This is R4. This is a reflection. If the angle of incidence in optically thick medium is greater than critical angle, in that case, the ray of light gets back to the same medium, same optically thick medium. If it is water, light gets back to the water. This is called as the total internal reflection. This is called as the total internal reflection. Okay, so the last I4, I mean the last ray diagram, I4O, OR4. So this is called as the total internal reflection. So what is this? If angle of incidence, if the angle of incidence in optically thick medium is greater than critical angle, theta c, the ray of light, in this case the ray of light gets back to the same medium, that means optically thick medium. If the angle of incidence in optically thick medium, this angle is greater than the critical angle, then the ray of light gets back to the same medium, same optically thick medium. This phenomenon is called total internal reflection. Total internal reflection. Okay, so this is the total internal reflection. Now people, they can ask you conceptual questions from here. Look at this. Let us suppose this is a pond. Okay, this is a pond. And this is a shore. The fisherman is here, standing there. And of course here is the water. And consider here is the fish. This is the fish. This is the considered normal line, and the fish, check the fisherman there. How? He look at this like this. Like this. This is the fish eye and this is the ray diagram, ray. What is this? This is angle of incidence in optically thick medium, water. Because this is air. Of course the fisherman is in the air, on the land there, so, and water there. So do you think the fish able to see the fisherman? If the ray go like this then, something like this, you can, right? But what happens, it depends on, look at this angle. If this angle is greater than theta c, for water, I think the critical angle is roughly 49 degrees. If this angle of incidence, let me call angle of incidence theta I. If theta I is greater than theta c, what happens? Then in that case, this ray cannot go there. This ray it simply reflects. Then the fish, he can see this point here. He can see the bottom of the pond then. he cannot see the fisherman. This is the total internal reflection. That means if the angle of incidence in optically thick medium is greater than critical angle, in that case, the ray cannot refract, it reflects. That is the total internal reflection. Okay. So we are talking about the refraction of light. There are many applications. We have to do the numerical problem also. Okay. But now I want to start the lenses. Okay. Because I already mentioned this is glass slab. We can observe the refraction of light here also, and we have other one. This is the lens. Okay, this is the lens. This is, look, we call this is convex lens. Okay, we have two types of lens. One is convex. Convex lens is, look, it is, if I touch this, it is thick in the middle. And there is another type, I didn't find the other one. The other one is concave lens. So basically we'll talk here about only two types of lens. One is convex lens, other one is concave lens, similar to the mirror. We have a concave mirror. Concave mirror is converging mirror, and other mirror is convex mirror. Convex mirror is diverging mirror. Everyone, this is a concave mirror. This is converging. This is converging mirror. Why? Because if you draw the ray diagram like this, what happened? After reflection, the light converges right there. That is why we call converging mirror. Other one, convex mirror, like this. So if you draw the ray diagram, what happened? After reflection, they diverge. That's why this is diverging. This is diverging mirror, this is converging mirror. But today I want to talk about the lenses. Lens. The lens is the transparent medium. The refraction takes place in lens also. And there are two types of lens. One is convex lens, and another one is concave lens. Okay, if I find the concave lens in my next class, I'll bring that. So the convex lens is like this, thick in the middle. If you touch this is a thick in the middle, and concave lens is thin in the middle. So convex lens, you can draw like this. This is a convex lens, and concave lens you can draw like this. This is convex lens, this is concave lens. Concave lens is thin in the middle. Convex lens is thick in the middle. Now the convex lens, we call this is converging mirror. Sorry, converging lens, not mirror. Converging lens, and this is diverging lens. Okay. So in these two types of lens, we have more, okay? But I told you that we'll talk only convex and concave. If you would like to know, there is another one like we call plano-convex lens. So look, this side is plane, this side is convex. So this is called as the plano-convex lens also. So you have a two reflecting surface, everyone. Look how it works is, if I draw the convex lens, look, you have one surface is like this sphere, and another one is this. So there is one center of curvature here, another center of curvature there. So actually you have a two spherical surface there. So one is this spherical surface, part of the spherical surface, another one is this. If you combine them, it is transparent. Now the convex lens is something like this. Okay, so in this case also, in case of convex lens and concave lens, we have to define the focal point, we have to define the principal axis, and we have to draw the ray diagram, we have to write down the lens equation, kind of similar to the mirror. But this lecture is done because my video is almost 1 hour long already, so I cannot make more than like 60 minutes. So I want to stop here, but I will continue this in my next video. Okay, thank you.